Okay, welcome back. Glad to see many stayed. So this is fantastic. So we are on to the last part of the workshop, and the first session will be Anirudh. Anirudh, please go ahead.
Yep, thanks. Do you see the presentation?
Great.
Awesome. Yeah, thanks a lot, and thanks everyone for sticking around. I know it's a bit late in the afternoon, and there's been a lot of information. So I'll try to keep this fairly high level. But it's really exciting to see, also for someone speaking personally for myself as someone who's part of the development team, just to like see all the different capabilities that are available. It's really kind of cool. So, but yeah, so this is the work that I'll be talking about today is kind of, it's still very much work in progress. So, we are happy to get any sort of, hear your thoughts, comments, as well as, show some initial, results that we have with multi-objective hyperparameter optimization, right? So let's just get straight into it. This is, I think, one of only 2 or 3 questions that I have. So what is multi-objective optimization? And the reason I put this is because I personally am primarily an optimizer, so I like to see a formulation, but this is as simple as it gets. And so the idea essentially here is that you have, instead of just one objective that you're minimizing over some domain capital X, you are instead trying to optimize several objectives. You're trying to find that one point in your domain which in some sense minimizes not just f1 of x, but f2, f3, fn, in general m objectives. And so before I get more into the weeds about this, why multiple objectives, right? So in reality, we know that the real world, we often don't just have one objective, right? So far in the entire, probably this entire last few talks that we have seen, we have been looking at some sort of validation loss, or some sort of prediction, some sort of metric of your model's predictive capability as the sole metric. But we know that when we actually deploy these models in practice, there are often several other metrics, right? Even if we look only within the domain of prediction performance, there are multiple such metrics, right? And here I just give an example of classical classification, ML, a classification model. So we know that it's, you might look at accuracy, for example, but we know that accuracy is often not the only metric. So for example, if you have a data set which is imbalanced, and let's take a classical binary classification model. If you have an imbalanced data set where 95% of the labels are positive, a model which is like the dumbest model, which only predicts always the positive class, which has a 95% occurrence, is going to be 95% accurate just because that's how the data set is. And so you have multiple metrics, right? So you can look at things like the precision. You can look at things like the true and false positive rate. So this is like the precision and recall. Also, other definitions being sensitivity or specificity. You can look at the AUC, which is the area under this curve that I've shown here on the right. So which is this. Sorry about that. Which is this ROC curve, so the receiver operator operating characteristic curve, where you're essentially plotting true positive versus false positives, right? So a perfect classifier, for example, has a true positive rate of 100% and a false positive rate of 0%. But we know you cannot build such a perfect classifier in practice. So a simple way of just understanding why this is, a multi-objective problem is, traditionally, if you take a 101 class in statistics or any machine learning class, you're going to, you learn about ROC curves, and we know that the more you are to the left and to the top, the better you are as a classifier. But then if you actually look at real world, ROC curves, you'll often have curves that kind of, intersect each other. So one curve might start out, being on top of the orange one, but then it might become lower, right? So, and then you can ask the question, okay, which of these two curves is actually, the better classifier? So which of these two classifier models is better? And the answer is that, it really depends, right? So you might want to actually look at both of these models and try to look at some other metrics and actually look at this from a multi-objective perspective to decide which model is better. There may be other metrics. So, I mean, so even if you, often one is, again, not just interested in looking at, some sort of predictor performance, but you might also be interested in computational, metrics or so-called deployment metrics. So what do I mean by that, right? So you might be interested in coming up with a neural net, which is not only accurate, but also which can, has a low number of flops. So this is kind of very interesting when you look at things like IoT or edge applications where you don't have a lot of computational power. And of course, I know that we have been talking a lot about, big machines, Summit and Perlmutter and whatnot. But then if you are actually interested in deploying this on a very low compute power, hardware, you might want to actually come up with a network which actually does a low number of flops, for example. Another example could be model size. So this actually came up in one of the in the earlier sessions. A question came up about memory requirements of of deep ensembles, right? So maybe you want a model size, maybe you want a model which has a low memory footprint. And so maybe you want to optimize for that explicitly, in addition to just your accuracy. You might maybe, for example, be interested in training time if your data is kind of or if you feel like you'll have to retrain your model. So maybe your neural network architecture is fixed, but then you kind of have to retrain the weights every once in a while, and so maybe the amount of time it takes to retrain is something that's important. Similarly, maybe prediction or inference time is maybe crucial, again, when we look at these kinds of edge applications. And so the final side to motivate why multiple objectives, that there can be objectives which are, again, beyond performance in terms of both prediction as well as computational, but maybe you're interested in things like fairness. Right, so and so there are well-defined, mathematically well-defined rigorous metrics for that, things like equalized odds and equal opportunity. And so this figure here essentially shows that, again, if you were to solely optimize for one objective, which is in this case, you're trying to decide what is the loan threshold at which you are going to offer different groups, and so this can just be like two different groups. Hypothetically speaking, there's a blue group and there's an orange group. You say that you'll offer the loan, to the blue group if they are above a certain threshold. This can be, for example, your credit score, and so you set the threshold at 61 for the blue group and 50 for the orange group, so as to maximize your profit. But then if you actually look at the true positive rate, which means in this context that of all the people who can pay back the loan in the blue group, turns out that your classifier is only offering the loan to 60% of them and 80% in the orange group, which means that your classifier is actually not fair, right? And so you're no longer does not have equal opportunity, so to speak. So you can actually make sure that the true positive rate across your different classes are equal, and so that can be, again, an additional objective in your model. There can also be metrics of you might also be interested in interpretability. And so maybe one way of making sure that your model is interpretable is just making sure that it's sparse. I mean, it's just one way of, it can be a proxy. It can be, for example, the number of features if you're doing like some sort of feature engineering. And it can also be robustness, right? So beyond fairness and interpretability, but maybe you want to make sure that your model is accurate to adversarial attacks, for example. All right, so I hope that kind of motivated that, why multi-object, like why you need to adopt a multi-objective approach, but what does it even mean to be optimal in this sense, right? So here's an example, here's a simple example. It's a one-dimensional function. You have just one objective, and anyone can tell you just looking at this function that the optimum is achieved at this particular configuration with this objective value. And if you have a second objective, again, if I just look at the second objective, this is, I can just look at it and say, okay, this is where the objective is. So which is the optimal configuration? Is it this point here, or is it this point here, right? And so the answer is that we don't know. And so what you can do actually is you can actually vary your X over the entire configuration space and plot the two objectives, essentially in what a physicist would call phase space, right? So you're looking at the two objectives and you exhaustively search all possible configurations and you see what are the attainable objectives, right? So this is the attainable objective set in phase space. And so now here it's interesting to note that you can actually look at the minimum F value that you can get, which is somewhere here, F1, which is somewhere here, and the minimum F2, which is somewhere there. But there is no single configuration that simultaneously minimizes both objectives, right? So attaining this kind of ideal goal where you simultaneously maybe minimize both your accuracy as well as you're fair to everyone, it's usually not possible. So what you can instead look at are these red points, right? And so this is what is called the Pareto front. And what this means is that these are essentially those points which actually dominate every other configuration. Because, for example, if I look at a point here, somewhere along this this configuration is actually has worse objective value compared to at least one point on the Pareto front, right? So, for example, we know that this point somewhere here on the red Pareto front is actually better than a point here with respect to both objectives. But the points on the red front are actually completely undominated, which means that you cannot really compare them because improving one objective along, for example, the F1 dimension means that you'll have to degrade the other one, right? So that's what is called the Pareto front. So one goal of multi-object optimization, so there are multiple goals. So one goal is actually to find one or more optimal points on this red front, also called the Pareto optimal or the Pareto efficient points. Another goal can be, for example, to find all possible or as many as you can Pareto optimal points, and with a goal to actually maximize the area that you cover by this, that is covered by this region with respect to some point. So this is also what is called the hypervolume. It's just a technical term, but it's essentially equivalent to maximizing the hypervolume, right? So there are in a sense two goals, right? So one is just find some point on this front, and the other can be try to find as many configurations as you can to present and ultimately let the application modeler decide which of these configurations to go for depending on the use case. All right. So how do we do this? Especially in the context of hyperparameter configuration, hyperparameter optimization. So there's one approach. There are two broad families of approaches. So in the first approach, what you can do is you can, for each of your objective functions. So we looked at validation loss, and and maybe you want to look at model size as a second objective. You can essentially fit a separate surrogate, right? So maybe you have a GP, for your validation loss, and maybe you have, I don't know, a separate GP or another, random forest for your other objective. And you can essentially try to fit a separate surrogate, right? And then you can try to write an acquisition function which maximizes, your hypervolume explicitly. And so what is the advantage? The advantage is that you're explicitly doing Bayesian optimization with a goal to find all possible Pareto optimal points. And so that's nice. But the problem is that it has a few, difficulties, which is that it's kind of hard to express preferences if you have, any preferences between your objective functions. And the second is that it kind of scales very poorly with the number of objectives. Well, for one, you're actually now, for as many objectives you have, you're actually going to fit m times as many surrogates in every iteration. And moreover, actually computing this hypervolume turns out to be quite hard in general, right? So it turns out to be exponential in the number of objectives. And of course, you can improve this worst case complexity from a theoretical perspective. There's probably some polylog factors missing here, but it still scales exponentially in general is the message here. So this can really break down your Bayesian optimizer, so to speak. So the second approach is to essentially combine these different objectives into one scale, into one single scalar, and then you can use traditional Bayesian optimization theory. So you can essentially, you say that, okay, I'm going to take all my different objectives, I'm going to, lump them up into one scalar. I'm going to fit a traditional, surrogate model that can be, your favorite surrogate model. And then you do Bayesian optimization as before. And so the advantage again here is that you can easily express your preferences because you can now say how exactly you're going to combine these objectives. And it also scales very well with a number of objectives, right? So because you're only fitting a single surrogate, and you can also use well-established theory. The caveat to this approach is that the way you actually, sorry about my mouse is being here, but the caveat with this approach is that so you're essentially somehow you're combining these objectives using some parametric way, which I've denoted here by this lambda. And so this parametric way in which you actually combine your objectives must be flexible enough that you can actually find all possible Pareto points, right? Or that you can at least explore the entire Pareto frontier. So that's one challenge. And the second is that you must now somehow come up with a scheme to explore different parameterizations of these, of combining these different objectives so that you actually find this set of this Pareto frontier. So that's where the challenges lie. So you gain some, but you lose some. And so this is actually the approach that we use within DeepHyper, again, because DeepHyper, the main focus of DeepHyper is scalability. And so we want to use an approach that is scalable, and we can actually work around this challenge here about trying to vary the scalarization to explore the Pareto fund. So here are, and like we mentioned before, this is kind of very much work in progress, but these are some examples of scalarizations that we are currently using within DeepHyper. Right. So what this is essentially showing, so the red curve is a hypothetical Pareto front. It never looks so nice in reality, but that's just as an example. And what these curves, these lines here are showing are just the contours of your scalarization, right? So the simplest thing you can think of is just doing a linear combination, but turns out this is not the best choice in practice. Because when you have Pareto fronts which look weird, which are non-convex and potentially disconnected, like the example that I showed you before, this linear combination does not work very well. So there are different examples. So you can actually work around that by doing, for example, a quadratic scalarization. You can look at, instead of a quadratic norm, you can look at some sort of a weighted infinity norm. You can also look at a weighted infinity and an L1 norm. And also you can look at other types of scalarizations, which I will not go into in detail. And so the idea essentially is that you essentially find, so this dashed line here essentially shows a direction along which you're searching. That's a scalarization. And then you can come up with different ways of actually exploring the region around that particular direction. And so in DeepHyper, you can either explicitly, specify this, one particular direction as well as a scalarization, or you can let it just search along different directions and be that as a configuration that you can specify into your Bayesian optimizer. And we'll discuss that in the hands-on. And so I'll just leave you with this. So this is again still something that we are working on, and so that's why this is not part of the hands-on. But how do you actually do decentralized Bayesian optimization, decentralized multi-objective Bayesian optimization? Right. So in the centralized case, just to remind you, you have a single manager which actually is in charge of the Bayesian optimizer, the surrogate model, and then your workers simply evaluate the objective functions. In the decentralized case, different workers have their own optimizers, and they are also evaluating their own black box, their black box functions, and they just communicate the true objective values, between them. So when you move to the multi-objective case, the cool thing that we are exploring is actually that different groups of workers are essentially, in charge of different scalarizations, right? So they are doing different scalarizations, which can be different scalar functions, or it can also be different parameterizations of these scalarization functions. So they're still exchanging information between them about, objective function values, but then they are in some sense exploring different parts of the Pareto front. So the advantage of this is that, again, you're you're combining the best of both worlds. You're strongly scalable because you're only fitting, each of these workers is only fitting one surrogate, so only one model as opposed to multiple objective functions. But at the same time, they're exploring different parts of the Pareto front, which makes this, again, very much scalable in terms of compute, number of compute nodes. All right. So in the hands-on, so what we are going to do is I can stop for some questions because the hands-on is going to be fairly short, relatively speaking. But we are going to essentially explore hyperparameter configurations that trade off. For example, we have been looking at validation loss, but we are actually going to see how we can actually also try to minimize the model size or the number of parameters in that you're training for. But I'll pause for some questions before moving on there. So if there are any questions, please feel free.